Let's talk about section 7.2. In this section, we are given an example to prove that the Lagrangian is actually more helpful than any other thing under the formula. So we are given this example of a simple pendulum rotating along or around a point we can call pivot because it's rotating around it. And we have to use Lagrangian's equation. So the length of the string is L. At the end of it, there's a mass M, and the angle, let's call it phi. Okay. So now, what do? Well, first of all, we have to identify a Lagrangian. We know that Lagrangian is equals to T minus U, in which T is the kinetic energy. So the kinetic energy is equals to 1/2 mv squared, which can be rewritten as 1/2 ml squared phi dot squared. And then the potential energy is equals to mg, h. Now, what is h? Well, if you actually look at this, h is this slit right here. So h is actually going to be the difference between the bottom of the rotation and the point on which the mass is at that point. So the bottom of the rotation is actually going to be equals to L, because this quantity is going to be equals to L, while instead this quantity over here will be equals to, let me do a little better, L cosine of phi. As you can see, L cosine of phi plus H, L cosine of phi plus H is equals to L. Okay, so that means that H is equals to L minus L cosine of phi, and therefore it's equals to L times 1 minus cosine of phi. Okay? Now, we can use this for our potential energy. Therefore, potential energy is going to be equals to mg, and since h is equal to this, we can say times L times 1 minus cosine of theta. Alright, now that we have our Lagrangian, let's rewrite it. So Lagrangian is equals to 1/2 m L squared, phi, let me write it a bit, phi dot squared minus mg L times 1 minus cosine of theta. Okay, so now that we get here, we have to rewrite the usual function. So partial derivative of L in terms of, it will be Q in our solution, or simply phi, because as you can notice, the only thing that is actually going to be a dot is going to be a phi, because there's no L dot, there's no G dot, there's no M dot. Because the only thing that changes is going to be the angle, equals to d over dt times partial derivative of L in terms of phi dot. So from the first side, we're going to get negative mg L times, then we're going to have a negative cosine. The derivative of negative cosine is going to be a positive, so sine of theta, and the derivative of 1 will be 0. So, and then on the other side, d over dt, the partial derivative of L in terms of phi dot, so we're going to take the first part only. So the derivative of this is going to be equals to ml phi L squared phi dot. And so if we solve this part again, this part stays the same, of course. We can even get rid of the parentheses at this point. Is equals to the derivative in terms of time, so it's going to be ml squared phi double dot. Now, what you can think about this is that this part over here is equals to our torque. Our moment of inertia, because moment of inertia is equals to our mass times the radius squared, which in our case is L, so it's equals to ml squared. Now, another thing we know is that the torque instead is equals to the most general solution you can have is going to be equals to RF sine of theta. And so in our case, R is equals to L, as we said, F is equals to mg, because the only force is the gravitational force. Sine of theta is going to be equals to our sine of phi, because in this case we use phi as an angle. So as you can see, it's the same thing as this. So we can rewrite it as torque. Also, this value, we said this value over here is equals to torque. And this value over here instead is the acceleration of the angle. So we can just call it angular acceleration. Let's just call it alpha, like the book says. So we're going to have torque is equals to I times alpha. Now, where does this negative sign come from and where does it go? Well, if you think about the pendulum, so we go back to this, we know that the torque is actually going to push in this, well, actually, to be precise, in this direction. Why? Well, because the torque is the force that is coming out from the force. So the mass is moving in this direction just because of the torque. But instead, the acceleration is in the opposite direction. So this one is going to be the torque, and this one is going to be the acceleration. The angular acceleration, because as we know, our object is slowing down. So therefore, it's going to go slow down. It's going to slow down with respect to the torque. And that is the reason why we have our negative in front that we can actually get rid of in our final formulation if we want to. So, as you can see, we proved that our pendulum is equals to torque times moment of inertia times the angular acceleration.